My name is Alon Kipnis. This talk is about a two-sample problem for high-dimensional multinomials and testing authorship. It is a joint work with my postdoc advisor David Donahoe. At the core of this talk is a method that in its basic form discriminates between two high-dimensional distributions. We will apply it to textual data and in particular to authorship attribution problems. I would like to motivate this talk from its application in authorship attribution, and I would like to focus on a particularly famous authorship attribution problem called the case of the Federalist Papers. The Federalist Papers are a series of essays written in the 18th century in support of the United States Constitution. They are important even today because judges use them to infer the original intent of the Constitution whenever there is some dispute on how to interpret it. Most importantly to our story, they were published anonymously. Later on, John Jay, Alexander Hamilton, and James Madison came forward as the authors of those essays. We know that each of them held respectful position later on in life. John Jay was the first Chief Justice of the Supreme Court, Hamilton was the first United States Secretary of Treasury, and Madison was the fourth president. Over the years, historians were able to determine the specifics of who wrote each paper, except for 12 papers over which a dispute between Hamilton and Madison remained. The issue was debated for about 120 years after the papers were written, until two statisticians, Fred Musteller and David Wallace, published this paper. In this paper, they studied 77 of the papers from different reasons, and they used statistical methods to assert their claims. Their conclusion is that all 12 disputed papers were written by Madison. This conclusion is today's consensus, and in order to prove it, I will play the following part from the musical Hamilton.
Would that be enough? Alexander joins forces with James Madison and John Jay to write a series of essays defending the new United States Constitution entitled the Federalist Papers. The plan was to write a total of 25 essays, the work divided evenly among the three men. In the end, they wrote 85 essays in the span of 6 months. John Jay got sick after writing 5. James Madison wrote 29. Hamilton wrote the other 51.
So the figures you've just heard in the musical are according to the work of Musteller and Wallace. Hamilton indeed wrote more papers than the other two, but not as much as he or other claim. The message here is that if, at least in Broadway, we believe that Musteller and Wallace were correct. So how did Musteller and Wallace reach their conclusion? Well, they discovered that individual authors have characteristic word frequencies on certain author-dependent words. So therefore, you can attribute the authorship of a document based on its similarity to one or another author's characteristic word frequencies. Over the years, people suggested other features or methods that can be used to assign authorship. For example, this list says that one option is to look at the distribution of sentence lengths or word patterns or story shapes. A famous work is by Tisted and Efron, which developed an estimator for the number of unseen species. In our case, it would translate to unseen words. Therefore, they could apply their estimator to determine whether a newly discovered poem was written by Shakespeare based on the number of new words in that poem. Quite recently, Mark Glickman and co-authors addressed a particular authorship problem between Lennon and McCartney in various Beatles songs. And if you will, there are also a few famous open mysteries in authorship. For example, who is Satoshi Nakamoto, the creator of the Bitcoin, or who wrote the Bible? Summarizing the existing techniques, there are approaches to authorship attribution. They are based on feature handcrafting or tuning. What I will show you today is a technique that can do authorship attribution without handcrafting or tuning. This brings us to the plan of today's talk. The first step is to describe the method, then to show you that it works well in authorship challenges, and then in the last two parts to analyze it, first from a theoretical point of view, where we propose a particular model, and then from a data science approach that tries to understand why our method succeeds even though our model is wrong. Now I will describe the method. First, let me explain what do I mean by an authorship attribution problem. We assume that we have two corpora, corp A and B. Each of them is of homogeneous authorship. We're given a new document and we would like to associate this document either with corpus A or corpus B in terms of authorship. Let's start with something simple. Assume that I have a similarity measure or a distance measure between a document and another document. And by extension, I can think about it as a similarity between a corpus and another corpus, or a document and a corpus, where we think about a corpus as one large document. With such a similarity measure, you already have a procedure to attribute authorship. You check the similarity of a document to each one of the corpora and associate it to whichever has better similarity. And here we will assume that better similarity means smaller score, smaller distance. There is a nice way to assess the performance of this attribution process. This is called the leave one out performance measurement. And to get it, what we do is we check the similarity of each document within the document of non-authorship to each one of the corpora. Although if we happen to test it against the corpus from which it was taken, we remove it from that corpus. So here the dashed line means that original corpus, the A corpus, without the document's I. This way we can check the similarity of each corpus against each corpora. A good similarity measure will have better similarity of each document to the corpus from which it was taken. In this case, to corpus A. We can do this similarity check in the leave one out manner to each document of our training set or document of non-authorship. We can even have a two-dimensional representation of the result by associating the x-coordinate to the similarity with respect to the corpus A and the y-coordinate to the similarity with respect to the corpus B. I remind you that everything is done using the leave one out manner, so if the document happens to be from corpus A, then in this test for the x-coordinate, we remove it from that corpus A. And in the next slide, I will show you a particular similarity measure that is the essence of this talk. When I apply it to the Federalist data, I get this picture. Here, the x-coordinate represents similarity with respect to Hamilton. The y-coordinate represents similarity with respect to Madison. Each dot in this figure represents a document. Take this one, for example. We know that it is taken from Hamilton corpus. This is why it is red. Its similarity to Hamilton is given by the x-axis, which is around here, around 5. Its similarity to Madison is the y-axis, which is around 8.5. So you see that it has better similarity to Hamilton corpus. Indeed, what you can see from this figure is that the distortion similarity measure that I will introduce to you does a good job in separating the two authors. And after you have the separation, you can associate each document to the correct author, for example, either by saying which one has better similarity, in which case you use the line y equals x shown here as your classifier. You can also do a better classifier, perhaps in this case, by perhaps moving this line and come up with association rule, which is slightly better in this case. But the message here is that the similarity measure does a good job in separating the two authors. Okay, so now what is the similarity measure between documents that I want to show you?
Let's describe it. We call it DHC. HC is for higher criticism, and I'll explain shortly why higher criticism come up here and what higher criticism means in this context. So the procedure that I'm describing has as input two documents. In the background, we have a vocabulary, which you can just think about it as the concatenation of all the words exist in both documents. And the output is a similarity measure. Smaller score means better similarity.
The method consists of two steps, and I will explain each step in detail. The first step is what we called word-by-word exact binomial test. Here we do many tests, one for each word in our vocabulary. Each test we apply the function binomial test. I will explain what it is shortly, with parameters that derived from word frequencies within the two documents. So it tells you that our method uses the so-called bag of words modeling of documents when it does the comparison. In the second step, we take the many outputs of the first one, combine them all into a single score using a formula that we call the higher criticism. And I will explain shortly where this formula is coming from and why it makes sense to use it in our case. Next, I will dive into these two steps and explain them in detail. We begin with the exact binomial test. This test takes as input three parameters, x, n, and p.
It returns the probability of observing x or something more extreme than x in a binomial experiment with number of trials n and probability of success p. Here is an illustration for a particular case. This is the probability mass function. X is represented by the dashed line, and the probability of observing x or something more extreme than x is represented by the red bars. So this function, the binomial test, returns the probability represented by the red bars.
This function is implemented in any statistical software package. This is how to find it in Python SciPy. The value returned by the function, meaning the probability represented by the red bars, is usually called a p-value.
So this binomial test serves our engine. We call this function multiple times. Each time that we call this function, we call it with these parameters. X is the number of occurrences of the word within document 1, n is the total number of occurrences of words across both documents, and the probability of success is the size of document 1 over the size of both documents minus these two correction terms that you will see how they come up shortly. But overall, we can think about the probability of success as the relative size of the document compared to the overall size of both documents. And you can see that this situation is symmetric in D1 and D2 because the properties of this binomial test. Okay, so we said that this test returns a p-value, or we can call it a p-value, but it's only formal p-value under a particular model. So under this model, where this is a really p-value, it will make perfectly sense to do what we do. Of course, we don't expect this model to be correct,
but we can still use the pipeline that follows from this model. We call this model a binomial word allocation model. This model states that the occurrence of each word over both documents is equally likely to occur in any location. In other words, if you tabulate the occurrence of each word in a database and you mark it according to the document in which you see that words, now you can take this database and sparkle it back over both documents. In this case, the number of words that will fall in the territory of document 1 has a binomial distribution with parameter n and p that are set here. Let me give you an example of two words from the Federalist data. The word expected appears 6 times in Madison corpus and 25 times in Hamilton corpus. The sizes of Hamilton corpus to Madison is about 70-30 towards Hamilton, which means that we expect number of occurrences of this word to be about 30% in Madison compared to Hamilton. Indeed, the p-value that is associated with this word under this model is 0.2, which is not too small, which means that the number of occurrences of this word is pretty much agreed with the model. The story is different for the word according. The word according appears much more in Madison corpus than Hamilton, whereas we expect it to be the opposite because we have more Hamilton text than Madison. This is why the p-value here is relatively small. The model finds the occurrence of the word according to be surprising. Surprising means that it serves as evidence against this model, against the fact that the words are equally distributed over the text using this binomial allocation principle. So this is the first step. It leaves us with many p-values, one per each word in the vocabulary.
The second stage takes these p-values and computes the higher criticism of those p-values. So the higher criticism is defined by this formula. Here, pi brackets 1 means the smallest p-value, pi brackets n means the largest, and the rest is just the orders of the p-values.
You can think about this formula as some goodness of fit of the empirical distribution of the p-values, which is represented here by their orders, against the uniform distribution, which is represented here by the value of the cumulative distribution function of the uniform distribution. So the difference in the numerator is associated with the vertical difference on this curve, the green curve. What the higher criticism looks for is the maximal deviation of the empirical distribution of the p-values from the uniform, but not on this scale, but on this one. Here on the right, what is called the higher criticism objective is a standardized version of the difference between the empirical CDF of the p-values and the uniform one. The value of the higher criticism is this maximal difference of the higher criticism curve. Now, if the p-values themselves has a uniform distribution, as is approximately the case if the model that we are assuming is correct, then the higher criticism itself behaves like the maximum of a uniform empirical process, which behaves like a Brownian bridge. The maximum for Brownian bridge is well known and is given by this iterated logarithm. So if your data gives you a value of higher criticism that is much larger than this log n, you can interpret that as an evidence against the fact that the p-values obeys a uniform distribution, which is an evidence against this binomial word allocation model. In other words, it tells us that the words do not behave this uniform scattering between the two documents, which should translate somehow, as we understand it, to an evidence against the fact that both documents were written by the same author. I want to emphasize that this is only the ideology that derives our pipeline. We don't have to assume that any of this is true in order to use this pipeline. The higher criticism itself has been studied quite extensively in the last 20 years or so. There are also many applications. And if you want to understand where this higher criticism is most useful, then it will be those subtle signal detection problems where you have many features over which the signal can possibly shows up, although in practice it only pops in very few features. And of course, you don't know which in advance. Even though on those features where it's actually present, then it is so weak that it's hard to distinguish that signal from noise. This is why those problems sometimes called needle in a haystack signal detection.
All right, so this is a summary of what is the similarity measure that I introduced. First is a word-by-word exact binomial test with a particular set of parameters. Second is the higher criticism of the results of the first step. We use it as a measure of similarity, and again, to emphasize, We purport to use this measure of similarity, although the underlying model is not assumed to be true. Now let's see how it performed in authorship challenges. This is the data from the Federalist. I showed you before the red and the blue part documents. Now I also added the disputed ones. And you can see from this figure that the disputed ones also have a better similarity to Madison. This is the same conclusion as Mostello and Wallace.
Let's apply the higher criticism test in another situation. In this case, we don't consider only two different authors. We consider 424 authors. So here we're taking the data from the largest copyright-free corpus known as the Gutenberg project. We downloaded almost 10,000 titles by many authors. We check each title against all the authors and associated that title to whichever has better similarity, where we follow those leave one out procedure. Here we compared the higher criticism to two other measures often used in information retrieval, like a chi-square test or cosine similarity. And you can see here that the higher criticism performed much better compared to these two other metrics.
Another case, this is a real competition setup. There is a test set and a training set, which means that you are only allowed to use the training set to, say, tune your model or to train your model. Of course, we have no training or tuning to do. So what we do is we only compare the similarity of a document from the test set to the documents from the training set. And when we do that, using the higher criticism, we achieve almost the best performance in this case. And just to emphasize that the other models are passively trained. So there's parameters there. In standard machine learning models, you have between 100 or 1 million parameters today. So there's many things to tweak and tune. In ours, there's none, which means that it also provides you perfect interpretability to how we get to the decision compared to a model with, say, 1 million parameters in which you have no idea what each parameter represents.
So yes, we are not optimal, but we never search for optimality. We only used our method as an unsupervised, untrained discriminator, and it just happens to perform super well for this particular challenge. When I do a halfway summary
of the talk, we interpreted the higher criticism score as a measure of similarity of word frequency table, and we discovered that this measure of similarity is useful in attributing authorship. What we'll do next is try to explain why. So we will do it in two separate situations. First, a theoretical situation. So we have an idealized model and we see how our tests perform in this model. And later on, we'll talk about particular caveat in the model when we try to apply it to real text, and we will try to address that as well. So first, let's see how it works in an idealized setup. And the idealized setup that I want to talk about is the problem of separating two multinomial distributions. So this problem says that you have two data sets. Each one is taken from a multinomial distribution, meaning just each item in your pool has a particular frequency. They're all summed to 1. And you want to test whether these two distributions are the same or not. This problem is pretty old as almost statistics itself. Pearson has the classical work where he also presented the chi-square statistic, which seems to be the way to go with this problem even today. In the last 20 years, people from computer science and information theory community picked up this problem as something that can be very interesting, particularly in the case where the number of samples from a distribution is much smaller than the support of the distribution, or the size of the alphabet, or the number of features. So these are all synonyms in our terminology. We call it also, in our case, is the size of the the dictionary, the size of the vocabulary, sorry. It also appears under very different names like distribution identity testing, multinomial closeness testing, etc. We will try to address this problem under a particular assumption. We will assume that the differences between the distribution is small, in the sense that in most cases, the distribution itself, the items themselves have the same frequency, have the same probability. Only few items have either higher or smaller probability. And we will also tune the differences to be small, so small that they are barely noticeable, which means that in some cases, all tests that you can perform distinguish between the two distributions will fail. In some cases, you will be able to distinguish between the two distributions. And what I will show you is whenever you can distinguish the two distributions, then you can use the higher criticism to do so. So in this case, formally what we say is that we start with some base distribution, we call it P. This is the red one, say, and we perturb P over some of the items. So with some probability, we will perturb, in most cases, we don't perturb P at all. In some cases, we will perturb it in epsilon fraction of the cases, either plus or minus. And this is just to say that we cannot go below 0 because those things represent frequencies. Okay, so this is just the maximum between 0 and this difference. The square root here means that the perturbation itself is done in the Hellinger distance, and there is a reason why we want to use the Hellinger distance for this problem. We can translate this multinomial sampling problem into a slightly different one. I mean, it's equivalent from a statistical perspective, but just has a different presentation. So instead of using testing whether our data came from two multinomial distribution, we test whether we sample from a particular Poisson distribution or a mixture of distributions. And we set up the parameters of the Poisson according to the actual frequencies times the size of the sample, with the mixture parameters are the same as the perturbation of the multinomial distribution. So if we need to summarize what is hypothesis testing problem, what we care about in this hypothesis testing problem is the intensity of the perturbation, which is parameters here by parameter R, the red one, and the rareness of the perturbation, or sometimes it is called the sparsity, which is parameterized by beta. So the larger the beta is, the more sparse the situation is. When the smaller the beta is, the more, say, dense the situation is, which means that we perturbing much more entries. And we set up the scaling of epsilon and the intensity such that this problem itself will become very difficult in some of the regime, but we will also be able to solve it in part of the regimes, depending whether R or beta whether R is large enough and whether beta is small enough. Okay, so this is a situation that was also studied in at least in the one sample case when we only try to compare the given data set to a particular Poisson distribution. This was studied by Arias, Castro, and Wan.
Our results predict a particular phase transition for this problem in the parameters R and beta controlling the intensity of the perturbation and its sparsity. By a phase transition, I mean that there is a particular region in the parameter space under which we can find a sequence of thresholds such that the probability of type 1 error plus type 2 error of the test will go to 0. On the other hand, in the complementary region, under any tuning of the test, the sum of type 1 plus type 2 error goes to 1. Our result says that there is a phase transition for the higher criticism in this setting, and it is described precisely by this two equations when we distinguish between a case of a large sample and small sample. The large sample case means that each word occurs at least log n times, whereas in the sparse case, each word occurs less than log n time, perhaps 0, or perhaps something which is very close to 1. Sometimes the large sample case is called the dense case because the resulting contingency table is dense, it has not many zeros, compared to the small sample case, which is sometimes referred to as the sparse case. And we will adopt this terminology of dense and sparse. Since I'm talking about phase transitions and curves, perhaps the best way to proceed is to go to a graphical description. This figure describes the phase transition curve in the large sample case, what we will call now the dense case. This figure tells you that if you set up the intensity parameter R and the sparsity parameter beta according to each point here on this configuration space, then the higher criticism test successfully separates the two above this curve. On the other hand, below this curve, the higher criticism test fails. Meaning, even though R and beta are set up such that two distributions are not the same, the higher criticism test cannot detect that. You can observe this theoretic phenomena in your own eyes if you take synthetic data generated from the two distribution separated by the parameters R and beta, and then tune a test to detect that situation against a null hypothesis in which the two distributions are the same. In this figure, green means many successes, red means little successes, and you see that the theoretic curve nicely separates the two regions. Let's try and connect this figure back to the data. Under the null hypothesis, marked here in red, we know that if we order and standardize the binomial allocation p-values, we get a process that is approximately a Brownian bridge. In particular, we know how the maximum of a Brownian bridge behaves, and we know also that it's not exceeding log n. And this behavior of the standardized empirical process of the p-values is shared across all the red area in this figure. On the other hand, if we go to the green area, then the standardized empirical process of the p-values behave something like the green curve here, which means that it maximum reaches a high value, particularly due to the smallest p-values concentrated on this figure on the left-hand side. This tells you that you can potentially separate the two hypotheses by setting up a threshold for the maximum of this empirical process. The maximum of this empirical process is the higher criticism. The theoretical engine underlying this result involved a characterization of the behavior of the p-values when their value gets small. In particular, we show that there's a function that describes their behavior under each of these cases. The phase transition curve is obtained by solving an optimization problem involving this function. Interestingly, you need to use different tools in order to characterize this function in the dense case compared to the sparse case.
You can also use the phase diagram to compare the distribution, compare the performance of the higher criticism to other tests in this case. So, for example, a Bonferroni test will only consider the smallest p-value, and you can see that the Bonferroni test achieves the same phase transition as the higher criticism for a large sparsity, but higher criticism is better in the small sparsity area, which means that there is a regime in which the higher criticism succeeds, whereas Bonferroni test fails. For the chi-square test, you see that it is not even shows up in the area where the action is. So the chi-square test asymptotically fails in all this area where Bonferroni and higher criticism succeed. There's a particular lower bound that is you can get from the one sample setting in which you compare the observable sample to non Poisson distribution. Perhaps it's a point to emphasize that our test is completely adaptive to the model parameter. We never assume that we know anything about beta, R, or P. And you can still separate the two hypotheses in the green area. So otherwise, the one sample setting assumes that you are given the baseline distribution P, and you're just trying to compare your samples to this baseline distribution. This assumption is obviously unreasonable in the authorship attribution situation, and perhaps you can argue that in most situations in life, it is unreasonable to know that you are given the exact baseline rate of some high dimensional distribution. Okay, so hopefully now I convinced you that this higher criticism test has attractive theoretical properties for the two sample problem of discriminating two multinomial distribution. The issue that remains is to understand why it works so well in authorship attribution, where the data itself is taken from text, even though we know that words do not obey the multinomial sampling model that the higher criticism is good at. Particularly, the main issue is that words itself, the text itself has topic structure. Its topic structure creates these dependencies between words or high variation of particular words, and it is quite puzzling why our test works so well, even though these things exist. And what I will do next, I will try to exploit a particular property of the higher criticism that can explain to us why it works well on real data. So this study will be completely empirical, or no, there are not going to be any theory here, but it shows you another attractive property of the method, that it is completely explainable. So what we will show you, that the words that the higher criticism, quote unquote, cares about in practice are also words that can be associated with author rather than with a topic. Okay, so they are autotypical words rather than topic-related words. So how can we reach such a conclusion?
Our first step is to look at word counts via a variance stabilizing transformation. This transformation is a common practice in data analysis. There are many kinds of variance stabilizing transformation. This is a popular one due to Anscombe. There is a lot of reasons why we want to use this variance stabilizing transformation, but to simplify things, I will just say that after using this transformation, it makes sense to look at the data using the traditional lens of linear discriminant analysis that only consider means and variance. Indeed, we look at the empirical mean and variances of words across a single corpus. Before we were just talking about theoretic model, now we are just talking about empirical mean and variances. We are particularly interested in the ratio of standard sigma over mu, the standard deviation over the mean of a word, which is what's sometimes called the coefficient of variation. Here is an example of words and their coefficient of variation from a particular corpus. These words are ordered by their coefficient of variation from left to right. And what you can see here is that word with low coefficient of variation seems to be not related to any particular topic, whereas words with large coefficient of variation like justice and war seems to be more topic related. And in what follows, we will use this observation as our definition of topic relatedness. Words with high coefficient of variation are topic related, whereas words with low coefficient of variation are autocharacteristic. And we want to understand what the words that the higher criticism, quote unquote, cares about most. In the definition of the higher criticism, there is an inherent threshold, and I want to explain now what it is. Remember that we interpreted the higher criticism objective as the discrepancy between the uniform distribution and the empirical distribution of the p-values. Based on this interpretation, we can say that the higher criticism selects, quote unquote, a group of p-values that speaks out most against the null hypothesis. There is some significance to this selection, and one case where it has been discussed is this paper by Donoho and Jin. In our authorship setting, each p-value corresponds to a word, and we would like to refer to the words selected these ways as words that the higher criticism cares about most. So now, in order to understand what are the words that higher criticism, quote unquote, cares about most, we will repeat the following multiple times. We will take a document and a corpus and we compare the two. We'll see what words falls below the higher criticism threshold. These are the words here marked in red. And what this experiment tries to show you is that the coefficient of variation of the red words, meaning the heights of the bars, is on average smaller than the coefficient of variation in the general population. Now, this is only the result of one test of a corpus against a document. In order to prove this trend, we will repeat this test many times. In every experiment, we look at the coefficient of variation, record the coefficient of variation associated with each p-value in a particular location after ordering the p-values, and average that. So this testing and averaging procedure leads us to this curve here. The dotted blue line represents the average value of the higher criticism threshold. And what you can see in this figure is that the higher criticism threshold looks like it's driving the trend of low coefficient of variation for words associated with the smallest p-values.
In other words, it shows us that the higher criticism tends to select words with low coefficient of variation across a corpus, and we interpret those words as auto-characteristic words.
It is also interesting to see what are those words that really get selected. In this case, we looked at the words get selected when you compare Hamilton corpus to Madison corpus. This gives us a list of 85 words. And it is now interesting to compare those words selected automatically by the higher criticism to the words selected manually by Mostello and Wallace. These words are shown here in red. The higher criticism selects almost all the words that were also selected by Mostello and Wallace. With that, I would like to summarize the talk. We started this talk by interpreting the higher criticism as a measure of similarity of word frequency tables associated with documents using the binomial word allocation idea. And we discovered that this higher criticism score is very useful in attributing authorship. In particular, it works well without any handcrafting or tuning. In fact, as I showed you now, it automatically selects a particular set of features which you can think about as discriminating most the two authors. We then took two complementary approaches to analyze our method. The first approach is an ideal setup where our two samples represented by two multinomials, where we assume that there are differences between the two multinomials are rare and weak. Here we characterize the asymptotic performance of the higher criticism test using a phase transition curve. The higher criticism succeeds above this curve and fails to detect below this curve. The second approach is pure data science because we didn't care about any model. All we cared about is the coefficient of variation across a corpus of the words. We exploited this threshold property of the higher criticism to understand how the coefficient of variation of the words the higher criticism cares about most behave in practice. What we discovered is that those words are associated with relatively low coefficient of variation, and it is reasonable to interpret that property to say that these words are not topic related. Namely, the higher criticism is less affected by words that are topic related. This is the end of the talk. You are welcome to explore publications and software packages associated with this work on my website.